Hello and welcome to part 2 of the acid base for chapter 15. Looking at strong electrolytes and about dissociation and what that actually means. So the concept about dissociation really comes down to this idea of having a molecule and beginning to break down into multiple forms. And specifically you have something like sodium chloride, which we already know is a ionic compound. And in this specific case, when you put it with water, it gets hydrated and you form your Na plus and Cl minus ions in an aqueous solution, meaning that it's dissolved in water. Strong electrolytes, generally speaking, have a very good conductors of electricity. And because they're in the liquid, they automatically begin to allow electrical currents to flow through these charged ions. A weak electrolyte is something that's not really dissociated. So the example here is going to be like acetic acid. Acetic acid is a very weak acid, and what makes it very weak is that this reaction actually does not really go forward. There is a little bit of the H plus and a little bit of the acetate ions, but not enough to really increase that, lower that pH level. And so in this specific case, this would be a very weak electrolyte. If you were to try to run current through it, the acetic acid would most likely, fairly dim that light. Strong acids are strong electrolytes, and because they dissociate 100%, you end up with that. So the example here is going to be hydrochloric acid. Hydrochloric acid creates hydronium and your Cl minus in an aqueous solution. And because of that, you create those ions that allows electrical current to actually go through. Now, this is actually a single reaction moving forward reaction because you don't really reverse this one, unlike the acetic acid. And the reason why is because, again, strong acids will dissociate about 100% of the time. Here's another example of nitric acid. Nitric acid, when put in with water, produces your hydronium and also produces your nitrate ions. And that's a great example of another one where it ends up going 100%. The other one is going to be your chlorate, hydrochlorate acids, and these are going to also form your chlorate ions as well. And here's your classic sulfuric acid, which is your diprotic. So memorize these strong acids because these are going to show up on and on and on. And knowing how to go about doing these is super important about how to identify your strong and your weaks. In all cases, you're going to form these hydronium ions, but you're also going to form these other free-floating ions that are going to allow electrical current to go through. Now, let's talk about some of your weak acids, which are electrolytes, which I already mentioned before. Hydrofluoric acid is a very weak acid. I mean, if you go down the group for group 17, you will find that the acidity actually increases as you go down a group. Hydrofluoric acid is very similar to acetic, but nevertheless, it has that double arrow, which means it doesn't really dissociate 100%, forming your fluorine ions. In this specific case, is illustrated with a double arrow indicator telling you what that is. The other example is nitrous acid. So instead of actually having nitric acid, which is HNO3, nitrous acid is HNO2, you also have a problem with this. And this actually has to do with this idea of, again, these oxygen atoms are in there. Sulfuric acids, this is actually an example of your secondary sulfuric acid. So H2SO4 is a strong acid, but if you take the HSO4 minus, what ends up happening in this case is you get that extra H doesn't want to donate out, doesn't want to dissociate. And so because of that, you form an actual fairly weak acid. So again, just keep in mind these diprotic acids. All right, water, as we already know, is actually a fairly weak acid. It's an amphoteric acid. If you add water with water, it generally doesn't really form a lot of hydroxide. It's a very small amount of it. That's why the reason that pH is 7 is because of that. And strong bases are also strong electrolytes. You can go ahead and run electrical current through them, and you can see some really interesting things. One of them being your sodium hydroxide with water forming your Na plus OH. This is a very strong one used in common titrations. And then you could see that when you add water to it, that's where you end up with that. But the solid itself is actually fairly, it's not conductive. Okay. Now, in this specific case, you definitely have to get the solids in water. So you can't use solid NaOH or solid potassium hydroxide. And these bases are generally going to be your alkali metals, so they're going to be very strong. So K plus and OH minus. Barium hydroxide is another one, and again, definitely we have that idea of your barium and your hydroxide ions being formed, and so make sure you're aware of those. Okay, now on the weak side, here's an example of a weak one. So hydrofluoric acid, however, when you take a look at the F minus, it's still also considered to be weak. So you're forming this conjugate here, which is HF and OH minus, but it's also a very weak electrolyte. And again, we're looking at the conjugates here for NO2, again for HNO2, very weak. And for your conjugate acid-base pairs, the conjugate base of a strong base has no measurable strength. So if we're taking a look at your strong acid, what ends up happening is when you get that conjugate base, it's actually not really that strong. H3O is the strongest acid that can exist in aqueous solution. So this is actually something to consider, that we're always measuring that H3O plus ion. So we're not really looking at some of the other ones because that's the one that actually gives that pH. And the hydroxide is the strongest base that can exist in the aqueous solution. So again, when that dissociates, we're always looking at that OH minus and that H3O. Alright, so this is a chart that I would suggest you go ahead and read and get really familiar with, because the more you understand this, the better it's going to be for you. Specifically talking about the conjugates and the strength. So on a strong acid side, if you take a look at something like perchloric acid, and you take a look at your perchlorate ion, right? What you're going to find out here is that these are actually going to be your stronger acids, and then your base strength actually is opposite. So these are actually pretty weak ones. But as you get closer to the bottom side of your conjugates, it's actually going to be a lot stronger. So something, for example, like sulfuric acid, which is a fairly strong acid, it would actually have a medium low conjugate base strength. So these would be actually your weaker ones. But as you get closer down to the bottom, what you're going to find is something like a water, for example, would actually have a stronger hydroxide base. Something like an ammonia, NH3, would have a very strong base like amide ion. Something like acetic acid, which is a fairly weak, would actually have a very strong acetate ion. And that's one of the reasons why this one actually acts as a kind of like a buffer. It's because you end up getting that CHOCOO minus versus a Cl. And this is something very interesting to see, that it's always going to be the opposite. So the weaker that acid is, the stronger that conjugate base is going to be. Okay. Now let's compare a picture here about strong acids versus a weak acid. On a strong acid at equilibrium, what you're going to have is equal amounts of your H plus and your Cl minus. And that kind of makes sense because as it begins to dissociate, you're going to form a lot of these H plus and Cl minuses. You can see that from this picture here. As you start seeing the water molecules and you start seeing your Cl minus ions, and then you have your strong acid being pretty much producing that Cl minus. On the weak acid, something interesting happens here. For example, HF, as I mentioned, is a fairly weak acid. Ends up doing is that you get more of the HF at equilibrium because it does not dissociate, but instead you get very small amounts of your hydrogen and of your fluorine here, indicated by these spheres. So keep that in mind, that for weak acids, you generally speaking are going to get very low amounts of your actual conjugates and also of your free floating ions. Alright, so let's do a couple problem sets here. The first one is going to be what is the pH of a 2 × 10 to the -3 molar solution of that? So very simple, straightforward equation. We're going to start using some of these pH formulas. Alright, so the first thing we have to understand that this is actually a very strong acid. HNO3 is nitric acid, and so you remember from that table it was high up there with hydrochloric. And because of that, we're going to go ahead and do the reaction where you form a full reaction moving forward, indicating that there's going to be an H3O and an NO3 minus ion. Now again, this is actually your conjugate base, which is actually going to be a weak one. However, you do have your H3O, which is a pretty strong ion. And so that's the reason why you always want to look for the H3O plus and the OH minus. Okay. Now, to start, you always write down the equation to show that what's the ratio of those hydroxides and obviously of those H3O hydroniums. Now, let's take a look at what you start off with real quick. What you're starting off with here is a 0.02 molar of nitric acid. So, again, a pretty low concentration. And then you're starting off at the start, you're starting off with the 0 H3O because you have not moved the reaction forward. Now your there's 0.0 molar of the ion, and also you have 0 for that. So what you want to do, and you don't really take a look at the water here because it's obviously still participating, but it's not really as important as the other ones. All right. When we end, we're going to be shifting this reaction. So the HNO3 is going to end up producing 0.002 of the H3O. And then you're also going to be producing a lot of the 0.002 of the NO3 minus. Now, if you go ahead and take the pH of that log, you should find out that the pH concentration is going to be the same for the H plus, which in this case is going to be H3O minus, which in this case will be 0.02. So again, we're using interchangeably this H3O plus, but that hydronium ion is actually what we're dealing with as this acid gets into the liquid. And so you find out that the pH value is going to be at 2.7, which is a very low, and it actually confirms our idea that this is actually a strong acid. And so in this specific case, you're pretty much going to be using a 2.7. So again, just showing you this idea of this equation. Normally people would just kind of plug and chug this and it would still work. All right, on the pH for the barium hydroxide, it's same idea, but now we'll have to take it one step further. We're going to be using and assuming it's actually going to be a base, same idea. And we'll be writing the equation now with the net ionics here. What you see is the barium is going to be dissociated into barium 2 plus, and then your 2OH minus. And that's to start off with. And again, we're going to do the exact same thing. 0.0118. We're going to put the 0.0, 0.0, 0.0, but then we're going to put the 0.18 and then also 0.18 on that side. So 0.036, sorry. Now the reason why we do here that 0.036 molar, not 0.18, boo here, is because you have a 2 molar solution of that. So out of that 0.18, you're going to end up producing 0.018, but instead of producing 0.18 on the hydroxide, you'll be doubling up using because you have 2 of those. Okay, so in this specific case, you would actually try to figure out the base form, so it'll be 0.036 molar of that, and you take the log of that to subtract it, which gives you a base of 12.56. So this is actually a really good example of something where you have to take into account the number of moles being produced as far as calculating the concentration for that acid. Okay. All right, let's talk about weak acids. Specifically, HA is denoted usually, and then also acid ionization constants. So this idea that you can get a weak acid is denoted by the HA, and again, I mean, this is just a general, symbol that they put out. You put in some water, you're going to form obviously your hydronium plus your A minus. Now what's going to happen here is that when you actually do the whole reaction, you're going to end up simplifying it down to HA plus equals to H plus and A minus. Obviously you're going to add in the water in here. It's going to be a straight on, ionic. And then you're going to use what I call the Ka formula. Ka formula is usually generally used for very weak acids. You don't really use it for strong acids because strong acids go 100%. So you're not really looking at ratios here, but on a Ka value, what you're looking for is that ratio. Okay. Now, Ka is called the acid ionization constant. It's also another name that comes out. It's basically how much of those ions you ionize. And generally what you do is you basically have to figure out what happens when Ka rises. So if Ka rises, the amount dissociated here rises as well. So for example, if I'm looking at a high Ka, the numerator is going to be high. It's going to have a high H plus, it's going to have a high A minus, and maybe probably a low HA. So generally speaking, the weak acid is going to have a stronger piece. It's not going to be as strong as something like a hydrochloric or as a nitric acid, but it'll be pretty strong. So here are some constants for some Ka values and conjugates. So for example, hydrofluoric acid, we already know it's a pretty weak acid. 10 to the negative 4, it's under 1, pretty weak, but its conjugate base is going to be 1.4 times 10 to the negative 1. And again, we're kind of not getting a lot of that because of the situation with the dissociation. Nitric acid, which you already know, it's a pretty weak acid as well. And again, your Kb value is going to be 2.2, so the amount of that gets, reduced as well. And so aspirin is also going to be a weak acid, and you can kind of see what happens with the Kb. So the Kb value for the conjugates are actually also very small. So that's something to really consider as we're kind of moving forward. All right, so let's do a couple more problems here. So what is the pH of a 0.5 molar of solution of 25? So this is actually another straightforward type of problem. All right, so your first step is to write the equation out. HF equals H plus plus F minus. And what ends up here is you get the Ka value for this. So what we need to do is figure out a couple of things. So you can't quite use the log function, and you can use that, but you have to take in consideration the Ka value for this. And so if you take a look at it, the Ka value, if you look it up a table, it's 7.1 times 10 to the negative 4. Now, since it is a weak acid and it ionizes into H plus plus F minus, we're going to have to try to figure out what that excuse me, H plus will be. So what we have is we have to do what we'll call the icebox method. Now the icebox method is going to go ahead and talk a little bit about how we're going to set this up as this weak acid begins to ionize. And so you're going to have three things called the initial, the second one called the change, and the third one being your equilibrium. So at initial you have 0.50 molar of your HF, which was given in the problem. Okay, now you have 0 of the H plus because the reaction has not moved forward, and then you end up with 0 of the F minus. Now at the change level, then obviously we're beginning to see a little bit of a shift. So now we don't know how much of it has changed based off of that. So we're going to know that by a minus X. So obviously it's going to be a negative because we're losing some of that HF to produce some of the H plus and to produce some of the F minus. Now by doing this, what we're going to have to do is figure out what happens at equilibrium when the reaction is moving forward. And so obviously we're going to denote that by 0.50 minus X because we're taking some of the X from that 0.50. And then we're denoting that with another X because that's going to go into your H plus and then obviously to your F minus. Now if you go ahead and do the Ka value for this, what you're going to do is you're going to get X squared divided by 0.50 minus X equals to 7.1 times 10 to the negative 4, indicating that we're actually using X here to multiply. We know that our K value is less than 1. So we can approximately state that the 0.5 minus X is approximately 0.5 here because you're not going to get a lot of this dissociating in. And so the 0.50 is going to be really close to 0.5. It may be even like 0.001 of it might actually move forward. So to simplify life a little bit, we're going to end up using that assumption of that 0.50 because it is a weak acid. And then we're going to keep the X squared. And at this point, it's a simple math. So once you solve for X squared, that gives you 3.55 times 10 to the negative 4. And then you should get as X equals 0.019 molar. And that's going to be your answer for that. However, they're looking for the pH value. So what we're going to do is we're going to assume that the number of H plus and F minus ions are the same because they're dissociating in equal amounts. And so what's going to happen is we're going to subtract that from the HF. And then from there, we're going to take that log. So what's going to happen here is we're going to use that number, the 0.019, okay? And if you subtract it from your 0.50, you should get a 0.48 molar of your HF. And once you do that, you should end up with the 1.72, which is the concentration for your HF. Okay. All right, so when can I use this approximation of 0.5 and minus that? And the answer is when the K value is generally less than 1. When X is less than 5% of the value, when you subtract it. So in other words, if we're taking a look at the concentration, the ratio, it has to be less than 5% of whatever it was. And so in our previous example, we have 0.019 as our X. You divide it by that 0.50 initial concentration, and you could see that it actually checks out. It's actually under 5%, which is 3.8. Less than 5%, the approximation is okay, but if it gets higher than 5%, you can't do that. Okay, so let's take a look at another example here. What is the pH of a 0.05 solution? So go ahead and take a couple minutes to do that. All right. So again, same idea. We're going to use a Ka value for x squared over 0.05. In this specific case, we're also estimating it. And we find out that your x is equal to 0.06. And we're going to double check in this specific case to see if it's actually over 5%. In this case, it is over 5%. So because of that, we cannot approximate any further. And so now we must use the quadratic equation to solve this instead, which is going to be a whole different thing. Okay. All right. So here we go. The first thing is when you're solving weak acids, you always want to look for ionizations that can affect the pH level. Second thing is you can always ignore the auto-ionization of water. You can ignore OH minus because usually you're trying to find H plus, so we don't really care about OH minus for that. And then you need to use ice to find the equilibrium concentrations in terms of X, but keeping aware of that 5% rule that we were talking about earlier. You're going to write Ka in terms of equilibrium concentration, solve for X, and if it's not valid, then you solve for X exactly, and if it is, then you calculate the concentrations using the pH values. Okay. All right, guys, we're going to stop it right there, and there'll be another part 3. Thank you.